Welcome back to the lecture series on bioelectrochemistry. In the last class, I highlighted the different kind of analytes which could be evaluated or which could be measured in the biological platform, especially in the critical care unit, and we talked about analytes like sodium, calcium, potassium, magnesium, oxygen, pH, glucose. So, today we will start off with the pH sensor, which is ion selective system, and it is very interesting if you look at the historically, and here what I will do. In the last class we talked about the metal electrode, and today with the ion selective electrode. So, what I am going to highlight is the basic concept. I am not going to go into the in depth detail of it, but the basic concept which I believe will help you. So, talking about the pH, what really pH measurement using an electrode is all about. All of you use pH, right, measurements in your lab. So, we know that pH is essentially hydrogen ion concentration, H plus. So, we have a neutral pH which is at 7. As H plus ion concentration, proton concentration increases, it is called as acidic. So, we go to 6, 5, 4, 3, 2, 1, 0, and if it is an alkaline, it goes to 8, 9, 10, 11, 12, 13, 14. Okay. So, OH minus ion concentration increases, but where was the genesis, where it all started? It all started in Germany in the year 1902, around 1902 or 1906. What was observed? So, here is the observation which is the most fundamental thing. So, around 1906. Okay. There was a student Kremer at Institute of Physiology at Munich, who discovered in 1906. So, that came from Kremer, who at Institute of Physiology in Munich discovered that a potential difference. So, this is the important part, a potential difference of 0.2 volt develop across glass, okay, across glass membrane, develop across glass membrane with acid on one side and neutral solution on other side. So, the student working with Fritz Haber in Karlsruhe 1908 improved the glass electrode and carried out the first acid based titration to be monitored with a glass electrode. So, essentially what you are observing is that suppose there is a glass membrane like this, okay, and on one side you have acid on one side, you have a neutral solution on the other side. Now, across it you are seeing you read a voltage. So, if you connect it like this, you will be reading a voltage. Now, if you know that voltage and if you know the molarity and molarity or whatever concentration of this. So, if you change the acid concentration, then you will see a change in the voltage. So, you can really use this system to say if this is the strength of the acid, this is the value of the voltage. If this is the strength of the acid or vice versa, if this is the strength of the neutral solution, then this is what I am going to see. So, this is the catch which led to what we call as the glass pH electrode. So, if you remember when I showed you the classification of the different kind of electrode, I talked to you about glass electrodes, for H plus ion concentration. So, this is that glass electrode what I am trying to discuss here is out here. So, essentially a glass electrode used to measure pH is the most common ion selective electrode. A typical pH combination electrode incorporating both glass and reference electrode whose line diagram is something like this. Now, I will put the line diagram on it, and the line diagram of this cell can be written as. So, you are using AgCl as the reference electrode, solid slash AgCl solid slash Cl aqueous. This is your outer reference electrode, outer reference electrode. Now, with H plus aqueous outside. Okay. Now, you have the glass membrane selectively bound to H plus outside glass electrode. This is your essentially this is your analyte solution. This is what you are going to measure, okay, with respect to this. Okay. Now, here you have the glass membrane, and this glass membrane has a property to selectively bind H plus ions. Now, with respect to this, you have H plus aqueous inside. Once I will draw the picture, it will kind of make sense with Cl minus aqueous. So, this is what we have as H plus inside glass electrode, H plus inside glass electrode, and then you have the inner reference, which is Cl AgCl solid Ag solid. So, this is your inner reference electrode, inner reference electrode. So, you have two reference electrode, inner reference electrode and the outer reference electrode. With these two inner reference electrode, whatever shift which is happening, which selectively binds. So, there is a change which you are seeing here as delta V, and that delta V is calibrated with H plus ion concentration. Based on that, we measure all our pH, and if you look at the picture of this thing, try to draw it for you, it looks something like this. With another inner chamber going through, and here you have a wire which is coming like this, another and this wire is going all the way down. You have another wire coming like from outside. It is okay. Now, this is the glass membrane is here. This is the glass membrane. This is the positive lid, this is the negative lid, leads to the pH meter, and here is the air inlet. This is the aqueous filling solution saturated with AgCl and KCl, and here you have beaker sitting there, which is the solution level of analyte in beaker. Level of analyte in beaker, and there are porous plugs which are a side kind of a problem, and out here you have 0.1 molar of HCl saturated with AgCl, okay. And the liquid level of the outer reference electrode is somewhere out here, and liquid level of the inner reference electrode is somewhere out here. These are the different liquid level, and AgCl paste suspended between the two sides of the fold. So, essentially what you see, it's kind of complex geometry, but as long as you understand this basic reactions, it should not be a problem for you to understand how the basic pH electrode works. So, these are the kind of glass electrodes which are used over the years for measuring the pH, figuring out the proton concentration, and this all starts with a very simple observation which dates back to 1906, this value, potential difference of 0.2 volt developed across glass membrane with acid on one side and neutral solution on the other side. Now, from here I will move on to another ion selective electrode today, which is a slightly complex one though. So, I will draw the electrode first this time before I. So, the ion selective electrode out here is something like this. Okay. Here we have. Okay. This is an ion selective electrode which is for potassium ions, okay. Selective binding of potassium ions, which is one of the analytes. And out here you have a reference electrode. So, this is your external reference electrode, and this is outside. Okay. Now, that is external reference electrode, this is ion selective electrode, ion selective electrode. You have internal reference which is out here. So, you realize there are different kind of references you have to put, internal reference out there, and your this is the filling solution inside, and outside what you have is where you have the analyte present. So, this is where your analyte will change its concentration, and this part which is the most critical part, this is your ion selective membrane, ion selective membrane. These ion selective membranes are immersed in aqueous solution containing analyte cation, which is say we say C plus, in this case C plus is equal to K plus what we are trying to measure. Typically, the membrane is made up of polyvinyl chloride. So, this is PVC, polyvinyl chloride it is made up of, impregnated with plasticizer which is diacetyl sebacet, a nonpolar liquid that softens the membrane and dissolve the ion selective ionophores. So, what is the ion selective ionophores here which are used? The ions for potassium measurement, there is something called valinomycin. Okay. Valinomycin. Valinomycin is ion selective material, okay, which is ion selective ionophores, and ion selective, this valinomycin is essentially is the ligand which is soluble inside the membrane and selectively bind the analyte ion in a potassium ion selective electrode. For example, we could use valinomycin. It is a natural antibiotic secreted by certain microorganism, and valinomycin, what it does is valinomycin binds to potassium ions. If this is the valinomycin ion, it binds to the potassium ions and carries it inside the cell membrane. Okay. The ligand which has to be chosen has to have a very higher binding to the XYZ analyte. So, what you are observing here is, say for example, I know the binding. So, I have external reference here, I have an ion selective electrode here, and I have an internal reference which is present there. Okay. So, with respect to the internal and external, I have a potential which could be measured. Now, if I know out here I have lot of valinomycin which are sitting there as analyte. Now, here if I change the potassium ion concentration, so automatically the binding of potassium ion concentration to the valinomycin is going to shift. Once that shift, the potential across this membrane is going to shift, because there is a mobility of the ions which is happening. So, if you remember, I told you there is no redox reaction as per se is taking place here. There is absolutely no redox reaction, but this is happening in a slightly different way. So, as long as you have something, so if you think of it logically, so what is happening is that here you have a beaker where you place your analyte, here you have a reference electrode along with your indicator electrode with respect to its reference. You have external reference and you have an internal reference, you have multiple references there. Now, you have a membrane out here. So, across this, across the electrode and outside, there is a potential which is maintained, delta E. Now, that delta is a function of the ion concentration outside. It could be I, okay, I could be plus or negative. Okay. It could be calcium, it could be potassium, it could be magnesium, it could be sodium, it could be chloride, whatsoever you wanted to. With respect to outside, there is a potential difference, but now if you add more of that ion, then the potential drop is going to shift, and if the potential drop shifts, if you already have a standard curve, you know that for this much ions. So, for that what you need on this membrane, a selective binder to a particular ion, and that is the key. So, in this case I gave you example of valinomycin, which is produced, it is a kind of a cyclic peptide which is there, which binds to the potassium and ferries it inside the cell. So, if you coat that membrane with valinomycin, what it will do? It will pull out the potassium ion and it will take it inside, and it will maintain an equilibrium. Now, if you add more, it will ferry more. If it ferries more, so automatically across this, there will be a concentration difference. Now, if you remember the concentration cell and all what I have taught, based on that, you can always calculate what is the concentration of the analyte. So, put the logic. I can give you examples after examples, but that is not important. Important is that you have to put the logics in place, what essentially is happening in this situation. So, this is the classic case of ion selective electrodes. Okay. From here, we will move on to, so as of now, if you realize, we are only talking about the change in the potential, but there are situations where you can utilize this technique by measuring the current, and that we will see once we talk about the oxygen and the glucose electrode. So, I will close in here, we will catch up in the next class. Thank you.